Remember the Egyptians used to weigh your heart against a feather to see if your soul was pure or not. We're going to use the same method to determine whether forces are balanced or not. And, well, let's set up a pretty common force diagram. We're going to have a block, and it's going to be pulled up this incline. So it's a block is being pulled up an incline by a string, and there's friction with friction. Okay, so we're going to set up the force diagrams here, and then we're going to try to balance them out and see what the equations lead us to. The first equation that we need to, the first force that we need to use is gravity. And I would highly recommend to color code your forces, because there's going to be pretty much a mess of a bunch of different forces. And if it's all in the same color, it's going to be a little confusing. So we're going to start here. Now, the force of gravity points down. And it's pretty important to remember that, well, we have to set up our coordinate systems. Turns out that I'm going to use this as our y-axis right here. This is the y, and this is the x. So that way I know if something's moving in the x direction, it's going to be along this direction. If something's moving in the y direction, it would be up and down this way. It turns out that gravity is twisted a little bit here, so that's why we're doing this sort of an interesting example here. Well, let's go ahead and see what the next force might be. That would be the normal force. That's this one that would be perpendicular to the floor over here. Now it's important to note that because these two, that this is not moving up and down on the y, that is agreed, right? It's not moving this direction, it's moving this direction. So these two forces must be the same distance. This length right here on the bottom side needs to be the same length as that top side, so that the forces are balanced and nothing moves along this particular axis. So we just need to make sure that we kind of draw that properly, and then we're going to write equations to make sure it's true as well. Okay, so that's going to be the normal force. Let's make sure to just kind of diagram these out. So the normal force, and then we have the force of gravity. There's another force. That's going to be the tension force over here. Now I'm going to make it a little bit bigger, because it's going to need to drag this box. And so we want to have a big tension force over here. This is with the string. All right. And then the final force, that's just going to be friction over here on this side. Kinetic friction. And those are going to be pretty much all the forces that are acting on this. And notice how this friction force is a little bit smaller than the tension force, because it's moving in this direction, so I wanted to represent that by giving smaller forces on this side, and even if I added those two up, it should still be, and then notice I said added those two up. What do you mean by two? I thought there was just one on this side. No, well, actually, there's two forces on this side. That's why I wanted to make a much, much bigger arrow here, because if I add up, isn't there a piece of gravity sticking out here as well? If I make it a little triangle here, you can see there's a little bit of this gravity as well. So that plus that combined is still not as large as this one on this T side. So I just wanted to draw out the correct sizes of these arrows to make sure that this was correct. Now, perhaps we can create some equations out of this. Let's start with the y direction. That would be this way. And we know that if we were to, ask ourselves, is it balanced, or unbalanced? That's the question we need to ask ourselves. Because if it's balanced, then we know that the two of them is not moving and is going to be equal to 0. That's the net. the net forces are going to be equal to 0. If we were to add these two together, subtract them 2, it would be equal to 0, and then, you know, and they would essentially be equal to each other. So we'll represent that in just a second. And then on the second side, we have unbalanced. So if it's unbalanced, then the forces, when you subtract them, they're just going to be equal to whatever's left over is going to be equal to MA. So let's try to represent that with some numbers here. In the y direction, Fy, we have the normal force, which is in blue. And then after that, we have to subtract the part of gravity that's sticking down here. This is going to be theta over here. Let's try to figure out what this is. Isn't this the adjacent side? Now we know the hypotenuse, and so in order to figure out the adjacent side, cosine theta equals, I'll call this y. Y over mg, turns out that y equals mg cosine theta. And if we were to flip that for x, mg sine theta. Just that's going to be for this one. That'll be for the next particular equation. So we can subtract from the normal force on this side, we can subtract mg cosine theta, because that's the y side. And if we were to subtract those, then our total answer after that would just be 0. That's the net force when we subtract these two is equal to 0. And we can just kind of rewrite this in sort of a way that n equals mg cosine theta. Doesn't this somewhat make sense? This is the balanced force right here. Balanced. These two are going to be the same size, same length. If we subtract them equal to 0, they must be equal to each other. It's balanced. They're not moving up and down across this axis, the y-axis. But let's take a look at the x-axis. So Fx, that's going to be equal to the tension over there. So let's take a look at T. Here's a capital T. And then we're going to be subtracting the force of friction on this side minus Fk. And then we also have a little bit of that gravity over there as well. So let's subtract that as well. Minus mg, that'd be sine theta here because it's the x direction. Now after all that's said and done, isn't there going to be a little bit left over there? So once we subtract all that stuff, there's a little bit of left over. That's going to be equal to ma because it's unbalanced. So now you can actually solve for like maybe acceleration if you kind of know the mass, right? And so these are the two equations that you can sort of derive from this particular, this would be unbalanced, and therefore moving. Okay, and this is not moving. Okay, along the y direction it's not moving, along the x direction it is moving. And so there you go. We sort of created a force diagram for this particular setup, this block being pulled up this hill with a string. We've got the tension in there, got a couple different forces, we got, you know, friction and stuff like that. So the keys are that, yeah, you have to have this x and y coordinate system developed. You need to understand that you got to balance out these equations with 0 and ma, and then also color code these. Color code it so that way it's not that confusing. It's a little bit more bright and visual. You can actually see what's happening. These things make sense. They're connected. So I understand how these force equations, these force diagrams may be a little bit complicated sometimes. So if you need help with creating a force diagram, you just leave a comment and maybe I'll make a video on one. So just check out the other playlists. If you enjoy watching these videos, make sure to like and subscribe.